Can everyone see this screen? So we all saw all this thing and we went into the programming. What we're going to learn for this semester, what's the name of the programming language? Programming language. Assembly language. Is it high level or low level? Why is it low level?
Because it's a long process.
We have to understand the architecture of before we can actually program. But when you say low, it doesn't mean it's a low or low level student. Then low level means from architecture based. And of course we saw some of the terms. So the next thing we're going to do is we're going to go in detail on the memory organization. Why? As I mentioned earlier, assembly language means requires you to understand the architecture of the hardware so that you know where to store the data and things like that. So therefore you need to know how the memory organization is actually structured. But before that, let us actually study the radix specification. Now what is radix specification? Radix specification is basically nothing but the base number. It's how you specify a particular base number. So we're going to actually see how we will define certain numbers. So we are going to use prefix. So there are a few numbering systems that we're going to see. One is actually hexadecimal. Then we're going to see decimal. And there is octal and also there is binary. Why we need this radix specification is because the assembler or the microcontroller won't know the value whether is it decimal or is it hex. For example, if you take 9, value 9. The value 9 exists in hexadecimal also there is 9, in decimal also there is 9. So which one? So you have to specify, make sure that this is hexa 9 or is it decimal 9. So how we use actually this, we use prefix. Prefix means something which you put in front, prefix. Postfix is something you put after. So for hex number, we'll use 0x, not OX, huh? It's 0x. So what does it mean if I put OX 77? The compiler or the assembler will actually read this as hex 77. Hex 77 and decimal 77 are not the same. You all know that, right? Hex 77 and decimal 77, they don't give the same value. If you perform conversion in the calculator, you'll know. The 77 will actually yield some other decimal value. So this is important. This is the prefix. This convention you need to know, this prefix convention, because you need to specify whether is it hex or any other number. So is it okay? For hex we use this prefix. This is not OX, this is 0x. So there's another way also you can use to represent hex number is by using capital H and single quote. This is also acceptable. Both are recognized. Either you write like this or you put capital H and single quote. It means this number is hexa 77. Is it clear? So for decimal number, you have to use capital D and a single quote as well. So when you write like this number 78 is decimal 78. Is it okay? Because here we are dealing with numbers. Of course, basically the hardware deals with binary. So whatever value that you write here, of course, it will be converted to binary. But if you don't define this properly, the converted value will be wrong. So this is for decimal, and for octal it goes the same. Octal you use capital O and then single quote. Is this okay? Is this okay? Can you understand? What is wrong with that?
9.
Yes. The character 9 is not allowable. So whenever you want to write, even in the particular number, make sure you write the valid values. So for octal, use capital O. decimal you use capital D. For hexadecimal is capital H or OX. So not OX, sorry, 0x. So most of the time this is very much we'll use this convention. This one, yes, whenever you want to use decimal. This one, no, we don't use it often. This one optional, but most of the time we tend to use this. And for binary, use capital B. So we can mention this. Is it okay? Quite simple, right? These are the prefixes that you need to know. Is it okay or not? Don't worry about where to use. Just need to understand that this prefix used for hex, this prefix used for octal, this prefix used for decimal, the other prefix used for binary. Easy? Done? So once we have to actually learn the static specification, then we'll move on to memory addressing. Now we're coming back to the subject of memory. Now we're going to see the architecture of the memory. Remember that for this particular microcontroller, it has two memory, right? What are those two memory? No, this program and also not. I'm not asking memory technology. I'm asking program. What type? How many memory? It has two. Data and also program. So it has two. So when you take a memory, memory is actually nothing but a sequence or directly addressable locations. So a location is referred to information in it, so that term is, we don't use it often. So this is the important thing. A memory location has two components, an address and its content. So let's take one example of a memory structure. When you take a memory structure, as I mentioned, it's like a shelf, right? It has a location and it should have an address. So this will be address 1, address 2, address 3. Is it okay? That means it should have unique address. So inside here you will have the content. Of course, in a while we'll see what is the actual address and what type of data that we can actually store. We'll see that as well. Is it okay? So this is the memory structure, and inside this memory structure is memory locations. So these memory locations, either you can use these few terms. One is you can use memory locations, or we can also use file register. File register is also a term which is used to refer to a memory location. What are the two terms that we use? Memory location and also file register. Are you all following? Is it the morning jet lag kind of thing? Didn't have your coffee. Is it okay? I think it's relatively simple enough. But if you don't understand, just let me know so I can know how to tell. So in each location, you can actually get store the content. So here. Now, in order for you to access this content, you must know the address. You need to provide the address so that you can access the content. It is just like mailing someone. You have the content of the mail. When you want to actually send it to someone, if you want to visit your friend in a house, is the content. But for you to go visit your friend, you need to know the address, right? So like in Chandi or Ilmu or Murni, all your apartments has a room. And it's a unique room, right? You don't see the same room. Hey, this one, hey, see, which one to go? All the rooms have a unique address. And in order for you to access to particular content or your people or your friend, you need to know the address. So those are the two things. You need the address and also its content. Is it simple enough? Okay or not okay? So now we're going to see the PIC 18 memory organization. Can I erase this part? Now the PIC 18 memory organization, you can see the data memory and the program memory are separated. They are not together. They are separate memories. Now this type of separation, because this architecture has a separated memory, this computer architecture, this is a CPU and this is your data memory and this is your program memory. Now because the memory are separated, this type of architecture is known as Harvard architecture. Harvard architecture. If you see in Chapter 1 in the textbook, in the end summary note, they have mentioned that this is Harvard architecture. Now there is also another architecture where they combine the program memory and data memory together. They are on a same memory space. Now that type of architecture is known as von Neumann architecture. Previously when I was studying here, we were actually studying Motorola MC68HC11, that model. Now that Motorola model or processor is actually a von Neumann architecture. That means in the same memory block there is an allocation to store program and there is an allocation to store data on the same memory. But this one, no, we have separate. Program memory is store all the program, data memory is store all the program. Now there is an advantage of having this kind of architecture and we will see in a while. So the separation of data memory and program memory makes possible the simultaneous access of data and instructions. Now this is known as pipelining. We'll actually study this later. So what do they mean by simultaneous access of data and instruction? So can you visualize this? So here you have your memory, data, and also you have your program. Now what is stored in program memory? Your program. What is stored here? Data. And here you have CPU, right? What's inside CPU? The control unit, ALU, and also the register, right? So as I mentioned earlier, when you want to execute a particular program, what does the control unit do? It will actually fetch the instructions from program memory, right? It will fetch one by one, it will come here, and then it will perform some task execution. Now most of the time the execution are done at data memory because all your data are stored here. So there are two phases in any task. First is the instruction fetching. I mean it fetches the instruction from here and decode it and it will decide to do. The action part is known as execution. That means it executes a particular task. Now the task could be anything like addition, subtraction, moving or whatever. There should be so many tasks, but I am not telling in detail because we are just learning some using basic terms. So there are two phases. What are those? Instruction fetching and also the task execution. So the instruction fetching is done from, it actually takes from here and bring it here. The execution will be done here. Are you following? Do you understand or don't understand? You don't understand or don't understand? Understand. Make it simple. Why complicate things? You don't understand, don't understand. If you understand, understand. But the thing is, if you don't understand, if you're keeping quiet, then actually you won't be alone, because if you don't understand, there will be so many others also don't understand. So when you ask questions, you're actually doing others and also yourself a favor. So because these two memories are separated, what pipelining means, it can fetch and it can execute at the same time. Because they are two separate memories, right? Of course, how it works is, of course, when you first start the microcontroller, of course, there's nothing to execute, because you have not even fetched the instruction. So in the first initial time, what it does, it fetches the first instruction here, right? When it has already fetched the first instruction, what happens to the PC? Do you remember? Yes, it increases and points to the next location, right? So after it has decoded this, it will execute here, right? While it is executing here, it can fetch the second instruction at the same time. So only for the first time, there's nothing to execute, it will just fetch. But for second time, it will fetch the next and execute the previous. So it happens at the same time. So that is known as
Pipe.
pipelining. Now, what about von Neumann architecture? What about shared memory? Now the thing with memory is, in a memory you can only access one location at one time. Memory is, you can only access one location at one time. So if you have a shared memory, that means the previous von Neumann architecture means you have a memory block, but half or certain portion is stored for program, certain stored for data. Are you all following? So if you want, imagine that this is actually a von Neumann architecture. So how when you start the microcontroller, what it does, because it's sharing the same block, it will actually will fetch the instruction first, it will decode and it will execute at the data storage part, and then only it can fetch the next. That means it has to wait for the execution first, then only it can fetch the next one. So it fetch and then it executes. After executing, then only it can fetch the next one. So do you see it is actually half times slower than pipelining? Do you get the idea? So that is the advantage of Harvard architecture. So in test 1, we like to ask this kind of question. Your understanding, what is the advantage of Harvard architecture? So you must explain. You can't search in notes. So there's no exact answer. There won't be an exact answer. It's just a matter of how you understand it. Is it okay? So the pipelining we will see later, but you understand the concept. So what kind of architecture we are dealing with? Harvard architecture. So data memory are used as general purpose register or special function registers. Now these two terms were asked in finals last semester. We'll see that also in a while. So what is general purpose register? The abbreviation is GPR. General purpose registers means, you see this data memory, or data structure. That means the structure or the content you can use to store any data. It's a general purpose register. From the name, it's a general purpose register. You can store any values. Now data memory also has special function registers, SFRs. Now these special function registers, take note that registers is also referring to file register or memory location. So there are three terminologies. Either they use register also is file, either register, file register or memory locations. They are all referring to memory locations only. So they also have a special function registers. Now from the name you know it's a special function registers. So you cannot simply load any value inside. You cannot just simply store any value because it will change the characteristics or the function of the CPU. We will see that later. We'll skip this now. So this diagram is very popular. Asked so many times. It's a very popular diagram. Take note that this is memory spaces. When they ask you to draw memory spaces, don't go and draw this. This is not memory spaces, it's a memory structure. So this is PIC 18 memory spaces. It's quite a famous question and never failed to be asked most of the time. So you need to understand. Later we will see all these details. We'll come back to this and see the details. So now let us focus on program memory. We're going to see the structure of program memory. Now this is program memory. So what we're going to do now is we're going to see how do we derive the address for program memory and what is the limit of the content. That's what we're going to see. I think we'll have time for that this morning. So I'm using PM, it's not a Prime Minister, it's the program memory. Okay. So every location has address and every memory location we can store contents. Is it okay? Now, program memory has a capacity of 2 megabyte. This is equals to how many byte? Do you know the terms byte? 1 byte is how many bits? 8 bits. 1 byte is 8 bits. 1 word? Okay, take note of these few terms. We have 1 byte. 1 byte is equals to 8 bits. Can you say that? 8 bits. 1 word is actually 2 bytes or 16 bits. 1 nibble, N-I-B-B-L-E, nibble is 4 bits. So again, 1 byte is 8 bits. 1 word is 2 bytes or 16 bits. 1 nibble is 4 bits. These are the terms. Okay. So the engine here you see it has given the capacity. The program memory has a capacity of 2 megabyte locations. So what is the value of mega here? That is where you are not right. In computer architecture, you cannot get 10 by the power of 6. It's not possible. It's because when you take binary number, it doesn't give you the flexibility of getting that value. 10 by the power of 6 is actually 100,000, right? It doesn't give you the flexible of getting that value because we are working on a binary. Binary doesn't have like 1, 2, 3, 4. It has 1, 2, 4, 8. Do you understand? It has 1, 2, 4, 8. Therefore, you cannot get the value in two binary system. There is no value of 1000. The closest value to 1000 is 1024. So 1 kilo is actually 1024 bytes. You didn't know this? No. Is it logic supposed to? So 1K is actually so mega means 1024 times 1024. So 2 megabyte means what? How many bytes we have? Can you do? 2 times 1024 times 1024. What's the value that you get? You can use the calculator. Are you all following? Is it okay up to this point? Unless if you don't get feedback, then I won't know. Okay. Okay. Sounds okay. What's the value? Come, we use calculator by taking so long. If 1 kilo is 1024 bytes, how much is 2 megabyte? So 2 times 1024 times 1024. Because kilo times kilo you get mega, right? What's the value? 2,090,000 something, right? What's the exact value? Can you just tell me? 209715. So the capacity of program memory is 2,097,152 bytes. Now what does it mean? In a while you will have the sense of it. Now, how much of data that you actually can store in one location? Now, as I mentioned earlier, that this PIC18 is how many bit microcontroller? Yes, it's 8-bit microcontroller. So, what does that mean? Yes? Yes? Yes, it can only process 8 bits of data length at one time. So, because it is an 8-bit microprocessor or microcontroller, the value, the maximum value that you can store in one location is, it makes sense. What? 8 bits, lah. Because you can only process the data of 8 bits, the maximum that you can store in one location should be 8 bits. As simple as that, makes simple sense, right? So that means in one location, you can actually store 8 bits of value. Means if in binary means you can store 0, 0, 0, 0, 0, 0, 0, 0. Is it okay? One location you can store that much of data. Now 1 bit is also equals to 1 byte, right? So that means one location you can store 1 byte. Now when we say the capacity of program memory is 2,097,152 bytes, what does it mean? Quite simple, I think. What is it? What? Come, can tell, no problem. Don't worry, why make so very making mistakes? Just try, lah. Come on, come on. If one location you can store 1 byte, and now the manufacturer says that program memory has a capacity of 2,097,152 bytes. What does it mean? Yes? That much of address. Okay? I think you try to say that much of locations. Same. So it means that when you say capacity, capacity means how much you can hold. So that means if the capacity is this much, how many locations we have? If one location stores 1 byte, if you can store 2,097,152 bytes, means how many locations we have? 2,097,152 bytes. So that's what it means. It's quite simple, right? Say the capacity is 2 million, means it can store 2 million bytes. Because one location is 1 byte, so you can store 2 million bytes. Is it okay? Okay. Now let us see. Now we know that we have 2 million locations. We want to derive the address. We want to derive the range of address. It is very important for us to understand this. Now let us take a simple example. Now the address, of course the address is going to be in binary. The address is going to be in binary. Why binary? Because in digital hardware, everything is actually in binary. But remember that we learned something about the compact representation. We will actually use that. So let's say if you have 8 houses. If you want to give address to these 8 houses in decimal, let's say the first house starts from 0. How do you actually address that? The first house you assign address 0. The second house you address 1. The 8th house you address it number 7. Is it okay? It's quite easy, right? Now instead of giving them address in decimal number, assume that we want to give them address in binary. So what would be the address of the first house? 0, 0, 0. First house? 0, 0, 1. Last house? 1, 1, 1. Do you get the idea? Now, for 8 houses for 8 houses, how many bits do you need to represent the address in binary? You understand the question? If we have 8 houses, and just now only we actually gave address in binary, right? How many bits do we require for the address? 4? Actually 3. 3 is enough. Because you have 8 houses. How do you get the value 3? How you derive where do you get the address 3? Just because I said it's 1, 2, 3. Why you say it's not 3? 0, 0, 0, 3. My question is how you get 3? How you know it's 3? Okay, that is one. That's one simple formula, right? Do you remember? 2 by the power of n equals to the number of possibility, right? 2 by the power of n gives the range. So in this case, it is actually 2 by the power of n. How many variations that do we have? 8 houses, right? So then you take logarithm on both sides and you divide. Then you get n equals to 3. This determines that for these 8 variations, in order for you to address the 8 locations uniquely, you need 3 bits. Now, do you understand this or not? Now, the same question I'm going to ask. If you have 2,097,152 locations, how many bits do you need to represent the address in binary? Is the question simple enough? Should say something. Tell me how many bits required. Do you understand what I just said? I mean, where's the mic? 16 million. You got the question? If for 8 variations or 8 locations we require 3 bits, now we have 2,097,152 locations. How many bits do we need in binary? First answer. Yes? Answer is 21. Everyone got 21? Did you take logarithm on both sides or have you forgotten how to use it later? Just take logarithm is 2 million divided by logarithm 2. What do you get? 21. You need 21 bits to actually represent that. What's the time now? 8:15. 8:50. Oh, 8:50. Yeah. Is it 8:50? Is it 8:50 already? Yes. So I'll just explain this one and I'm not taking attendance set, but I haven't updated. So since we need 21 bits, just now we saw 7, right? Very quickly let me finish this. 7 for the 8 locations, how we address them? 000, 001 until 111. So the same principle, now you need 21 bits. So 21 bits means the first address will be this is the starting address. The next one will be 0, 0, 0. Like that, you keep incrementing until you get the maximum. This is where the inmates thing, put in the box. So the maximum goes here. So if you notice that the address in binary, it is too much for us to actually handle. Do you understand how we actually got this in the first place? This is one of the most important things. If you don't understand, you're going to have a lot of difficulty later on. So better done. So because this is difficult for us to see and it's too long, we are going to represent the address in hex. That means instead of writing like this, how we convert this to hex? Every 4 bits becomes 1 hex bit, right? So this is 4 becomes 1, 4 becomes 1, 4 becomes 1, 4 becomes 1, 4. And the last one was maintained 0. So this whole address you can actually write as you have 1, 2, 3, 4, 5 zeros, and the last 0, 21, 0 becomes this 0, and this one becomes 1, F, 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 F. So this is the range of the address from hex 0, 0, 0, 0, 0, 0 until 1 F, F, F. Why this one becomes 1 F, F, F? Because of this one. This is 1 F, 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 F. Okay, we'll see in detail in our next class. So if there's any question, as I mentioned, please do clear your doubts the same week itself. Of course, when I say this week, I won't be here, both onwards. But nevertheless, you can actually email me. Okay, if there's no question, thank you very much for coming. See you all next week. There's no tutorial tomorrow.
Yeah.
Below.